The idea of conversion is very, very important. And there's a couple of reasons why. It says measurements cannot always be done in the standard units. A lot of times we're going to measure things, not really in circumference and diameter, we can, but really we're going to measure things in things like milliliters, because that's what we can easily measure with a graduated cylinder. However, a lot of the times we can't do our calculations in milliliters because it won't work as in terms of the math. So instead we need to convert to the standard unit of a liter. Or we talk about things in grams, but we really need to be in kilograms when we refer to energy. So there's a lot of times when we measure something that we actually can't do the math that we're trying to do in the measured unit. So we need to be able to convert. And a lot of times that's because we have something called a fundamental constant. We have these ideas of fundamental constants or things that are constant throughout nature that we will do calculations with. An example of that is the speed of light. So the speed of light is 3 times 10 to the 8th meters per second. Well, now, if I'm trying to relate something that I've measured that's in centimeters, I can't really put these two things together because they don't match. So it's really important that you be able to convert between units. And in fact, there is a very, very specific method of conversion that you are going to be required to do in this class, and that is called dimensional analysis. Okay, you can't do that. You are no longer able to do this King Henry died nonsense. Okay, yes, it works. You can move the decimal over. But the conversions that you're going to be doing are more complex than that, and so you need to start the process of this dimensional analysis. This dimensional analysis will be the key to your success in the second semester. So we're going to work with it in the first semester to show you things that you're comfortable with. Say, I know how to do this, and we're going to show you how to do dimensional analysis with it to make it work. But really, this right here, the idea of dimensional analysis, will get you through almost the entire second semester of chemistry. So, as far as metric conversions are concerned, you need to know these metric conversions right here. Okay? From giga to nano. If you look, the only one that's not a multiple of 3 is centi. And centi you should know for several different reasons. But you should already know what centi is. But giga is just a billion. So if you have a gigameter, it's a billion meters. If you have a gigaliter, it's a billion liters. Mega is a million. If you have a megahertz, it's a million hertz. And you don't necessarily have to know what these things are. In fact, you probably don't know what many of them are. All you have to know is that it's a base unit, and if I have a mega anything, it's a million of those things. If I have a kilogram, it's 1,000 grams. If I have a centigram, and then we reverse it, it's 100 of those equals 1 gram. Okay, if you notice right here in between killi and centi, we've changed this conversion factor. It's gone from times 10 to the ninth to times 10 to the minus. So it's the whole idea of that scientific notation and moving your decimal one way or the other. Now, let's look at an example so we can start to get into the idea of dimensional analysis. So this first one says how many milliliters are in a gallon of milk, and then it says that a gallon of milk is 3.78 liters. A lot of you can do this in your head, and you can say, oh yeah, milli and liters, and you can get what it is, and you'd say it's 3,780 milliliters, and that is correct. However, on some sort of work or some sort of quiz, you would not get full credit for this because you didn't show your work effectively. And you can't even just say, well, I'd move the decimal. You are going to be required to show dimensional analysis in the sense that you would start with what you're given. I'm given 1 gallon of milk. And then what you do is you set up a series of equivalences. Okay? This unit right here is on the top. It has to go in the next box on the bottom. Well, it doesn't have to be in the next box, but it's got to be on the bottom. And what I have is 1 gallon. Now I want to say what 1 gallon is equal to. And 1 gallon is equal to 3.78 liters. These are what are called conversion factors. These things are two things that are equal. Anytime that you have two things that are equal, you can put one above the other in a dimensional analysis. Now, if circumstances called for something different, there may be a situation in which gallons would be on the top and liters would be on the bottom. But that's not for this particular situation. The last thing that I need to do is I need to be able to convert between liters and milliliters. And if you look, liters and milliliters. Now you should know, based on the previous thing, that 1 liter is 1,000 milliliters. So now we can do dimensional analysis and we can say I've got gallons on the top I've got gallons on the bottom. This is like a big divide sign. Well, if you have something on the top and something on the bottom, they cancel out. Now, if you notice, only the units are canceling out, not the numbers. I've got liters on the top, I've got liters on the bottom, and it cancels out. The only unit that is left is milliliters. Now you multiply the numbers across because everything is gone except for the numbers. So you would say 1 times 3.78 times 1,000 divided by 1 divided by 1. And when you do that, you get the same answer that you would have done if you moved the decimal over, 3,780 milliliters. And this can be frustrating for some people. I totally understand that because they say, well, I can just move the decimal and be done. If you can get this process down, you're going to be successful in the class. So start with what you know and try and apply this method to what you already know and check your answers. If we look at another one, it says a weightlifter is capable of bench pressing 250 pounds. You always start off with what you're given, 250 pounds. The next thing you do is pounds has to go on the bottom. We want to go to the metric unit, which is kilograms. Kilograms is the standard unit of mass. And so we need the conversion factor between those two, and you can refer to the conversion factor in your packet, but we know that 1 kilogram is 2.2 pounds. So now we're in the standard unit of kilograms, and that's actually part of the answer. So I can multiply this out, or 250 times 1 divided by 2.2, and that will actually give me the mass that I'm looking for the first part, 114 kilograms. That right there is the standard metric unit. However, the second part of the question says, in the units most often used in chemistry. Mass, generally speaking, in chemistry is in grams. And the reason is we tend to deal with small samples. It doesn't make sense to put something as 0.0134 kilograms most of the time in chemistry when you can just say it's 13.4 grams. So because of the sample size that we tend to deal with in chemistry, we tend to put things in grams. So I need to go ahead and convert from kilograms to grams. So I put kilograms on the bottom, I put grams on the top, and I would know my conversion factor would be 1,000 grams is 1 kilogram. Pounds cancels, kilograms cancels, and I'm left with just grams. Multiply by the top, divide by the bottom, and when I do that, I get 114,000 grams. So those are my two answers for this particular question. The final example that we have for metric conversions says gold has a density of 19.3 grams per centimeter cubed. How many kilograms per meter cubed would this be? Now these tend to be the sort of things that you see conversion-wise in chemistry. So we're talking about density. This right here is what I'm given. But remember, when you see 19.3 grams per centimeter cubed, what that really means is 19.3 grams per 1 centimeter cubed. Now, a lot of the times we'll leave off the 1 because we see it as not being relevant. They say, well, it's just divided, it kind of cancels out, and they're right. But it is nice to say, okay, this is the equivalent of that. Now, what I need to do is I need to be able to convert from grams to kilograms. So now I say grams on the bottom, kilograms on the top, and now 1 goes on the top and 1,000 goes on the bottom. If you notice, that's different than what I had in the previous example. It doesn't matter which order you have these in unless it's a particular example. So because grams is on top here, grams needs to be on bottom there so that they cancel out. If you have 2 grams on the top, they won't cancel out. Now we look at the next one. I can go ahead and convert centimeters. Let me go ahead and change color so you can see it a little better. I can say that 1 centimeter is equal to, 100 centimeters is equal to 1 meter. And you guys should know that 100 centimeters is 1 meter. But now you may be asking yourself, well, what about 1 centimeter cubed? It should be the same, 100 to 1. And it's not, because what you're doing is you're cubing centimeters. But really, when you're cubing centimeters, you're saying 100 by 100 by 100. So really, you're cubing the number as well. So it should be 100 cubed on the top. Now on the bottom, you're cubing meters, but 1 cube is still 1. So when you multiply this thing out, you've got grams and grams, that's going to cancel. You have centimeters cubed and centimeters cubed, and that's going to cancel. So now you have to take a look at the numbers. If you look at the numbers, you have 19.3 times 100 cubed divided by 1,000. Now when you put that into your calculator, you should get something along the lines of 19,300 kilograms per meter. Now, if you're still struggling with this, I would really recommend that you go ahead and take a try at some of the examples and see how you're doing with the idea of dimensional analysis.